Assalamu alaikum. I want to start by thanking the organizers, of course, for giving me the opportunity to present here. So here you see the authors. Sorry, initially there was the transition metals. The metals was missing in the title, so the support will be in this talk always transition metals. And this is a collaboration with experimentalists. Most of the people on this slide are experimentalists, except Marcia Leonocci, who was a colleague when I was still at the University of Zurich, and myself, and the rest, they are either growing and characterizing materials. There's also Mike Altman and Thomas Gräber, who are very well known, also in Morocco. They come often here, and who wouldn't. So it's about the growth of high-quality hexagon boron nitrides on large scales. So the goal is to have a large-scale samples of the HBN, and I hope by the end you will see the advantage that they have made in the experimental field. And then our role is to support the experiments by some calculations. And the calculation I use the type DFT, density function theory. So the HBN, maybe you know already the properties. So it's a polar material, of course, boron and nitrogen. They have different electronegativity, but it's insulating. It has a large band gap. So although the structure looks exactly the same as graphene, because you have these alternating atoms or elements, and you have the polarity, there's band gap. So this material is insulating, and it's foreseen, and it is being used as an dielectric insulator. For example, in this case, you saw we have something on transition metal, so we put HBN in between to isolate the, for example, an adsorb molecule from the electron structure to metal beneath. So that's one of the roles of HBN. And it's very hard, like graphene. So it consists of the sp2 bonds in the plane. So it's very, very hard to break it. Of course, you can bend it, but it's harder to really break it. And it also exists as a 3D bulk material, but here we are interested in the 2D dimensional variant. And then when you grow these things on surfaces, so this is the rigid layer on a surface, and if the lattice constant does not match the lattice constant or the nearest neighbor distance of the substrate, there's usually this thing called moire structure which appears. Maybe you are familiar with this. One example is it's similar to what is shown on the left. If it's 2 layers of graphene, if you have this magic angle, you make it superconducting. So you have a bilayer of graphene and you make it superconducting because you have just the right angle between those two. And now here the difference comes from the different lattice constants of the HBN and the support. There are some cases where the lattice constant is the same, but usually it's different. So we will have in most cases we have a different periodicity of the HBN and the substrate, and it causes this kind of moire, or it's also called the superlattice. So the periodicity is not 1 by 1, but it's larger. You have more unit cells of the substrate and more unit cells of the HBN to make the lattices match, and this causes the moire, or gives rise to the moire. And the size of the moire, well, it depends on the lattice mismatch. So how different are the nearest neighbor distances in the HBN and the substrate, and the strength of the interaction. So whether the HBN adsorbs strongly or weakly on the surface. And here's an early example. So this was the so-called nanomesh. So it's Thomas Gräber, Hugh Kostwald, and their colleagues, entitled Nanomesh, and this is the STM image. So surface science techniques used to characterize this structure. And here then is an early example to try to functionalize this. So using the HBN and this larger periodicity, in this case it's something like the size of the so-called pores. These regions is something like 2 nanometers, so some molecules they match exactly in one of these pores, and the distance is something like 3 nanometers. And the idea is that using these as templates, so you can good selectively adsorb molecules at positions where you want, and then try to functionalize, for example, create the interaction between the molecules. So that's one of the goals also with the HBN and these moire structures. There's a review, quite recent review by Billy Auwerter about the HBN as found on the different metal substrates. So then I will quickly mention this. There's also a history, prehistory for HBN on iridium. I will just keep it very shortly. This was the motivation, and you see it's already 10 years ago. This was a German Physical Society meeting, and we studied a collaboration with some experimentalists also to study this, because there was somewhat a mismatch or misunderstanding about the structures. So it's a HBN, again, on a transistor metal. So the first results that I want to show, I will not go into any detail, basically, because I don't have the time and I don't want to bore you with the details. If you're interested, of course, you can contact me or Honja or Thomas or Mike Altman, the experimentalist. This was the first, well, not first, but first demonstration how to create a HBN of high quality on in a large scale and to transfer it to another substrate. Because the problem is that the HBN on these transistor metals, it's, of course, it feels still the electron structure beneath. And if you want to transfer it to some other substrate, how to do it? And they demonstrated this method, so-called distillation. And I try to go it very quickly. So this is the original structure. It's the same as I showed before. So it's HBN on rhodium-111, the metals are both. And that's the initial state. And then they detach it from the surface. They put it onto some other substrate. Here they just demonstrate. They put it back on the rhodium. But nowadays they can put it on different substrates. They put it on the rhodium, and this is the so-called TBN, so it's transferred BN. But it has more defects, for example, as you see here. And what they then do is that they do another annealing, and they see that they have this so-called distilled HBN, and it's of the same quality as the original one. So the idea is to show that you could grow this HBN on one substrate. In this case, they use mostly the rhodium-111, and then transfer it to another surface, and then by annealing, you get this metastable HBN first, and then when you go high enough in temperature, you get this distilled, or again, high quality boron nitride on a different substrate. So this is just some results. I will again not go into any details. This is a lower energy electron microscope for the specialty of Mike Altman in Hong Kong. So there you can see these different regions as a function of time, how these different regions then change when you heat the system or you anneal the system. Another probe for the structure is the ultraviolet photoelectron spectroscopy, so just shining light and looking at the signal coming out. And this is the original HBN nanomesh. And you have these two specific sigma bands at some electron volts below the Fermi energy. Fermi energy is at 0. So these are characteristic for the HBN. And these correspond to these two specific regions. I mentioned the pore, and then there's the so-called bio regions. So there are two regions where the HBN is at different height, and they give a different binding energy. And then in this metastable one, MBN, they have the binding, and the binding energy is different. So chemically, it's at a different state than in the original HBN. And this is then the model Marcello Iannucci calculated for the metastable boron nitride. So it is another more or less structure, different periodicity, and maybe you can see here some of the nitrogen atoms, they bind to the top sides of the transistor metal, so there's a certain curvature, and this gives rise to the more or less structure also seen in the STM. Then the second example I want to show about the growth, this is now HBN growing on platinum-111, a different substrate. It has different interaction strength, different lattice constant, and we wanted to look how this affects the growth of HBN. And one has to remember there's usually always also carbon dissolved into the bulk of the transition metal. So here one has to be careful. Then one has not only boron and nitrogen, but often there's also carbon which comes from the substrate if the substrate was not very or ultra clean before the experiment. And here then some experimental results. I have no time to go into details. Well, you see different structures. Again, this is the initial structure after the growth, and then different annealing temperatures. And this is the so-called lead, which shows the porosity in the reciprocal space. And the other probe I show, again, no time to go into details, but this is the X-ray photoelectron spectroscopy. So we see different binding energy in the core orbitals depending on the chemical state that the atoms are in. And this is specific for different elements. Usually they are different energies, so you see that energy scale is completely different. This is boron, nitrogen, carbon, and oxygen. And you see the signal. There's a signal then at the specific energies. Here one was just interested how much of these elements there are on the surface, so not in which chemical state they are. And the colors are the same as here, so the annealing temperature. So one starts from the initial one, so that's a black one, and then when one heats it up, then the curves are just displaced toward the bottom. So the highest annealing temperature is the red one at the bottom. And initially there's of course boron, nitrogen. They were the elements that were grown on the surface, but then there appears also some carbon. And as a function of the temperature, first you see that the boron is disappearing from the surface because the signal, the magnitude at this energy disappears. Then the nitrogen starts to disappear. But the signal of carbon remains strong, and it even increases. And the oxygen, there's some oxygen initially, some impurity probably, but it disappears also at reasonably low annealing temperatures. So first oxygen disappears, then boron, nitrogen, but the carbon stays until the highest annealing temperature. So here it's 1080 degrees Celsius. So what happens is that initially you grow HBN on the substrate, but when you heat it high enough, then something happens. Probably there's some desorption, and there's the carbon which comes from the substrate. And the carbon binds stronger than the HBN. Carbon, well, it turns into graphene on the substrate. Yeah, this actually, if you didn't know, maybe some of you didn't know, this was actually probably one of the first types of graphene which was created. People just didn't know. I mean, it was much before the Scotch tape experiments. But of course they didn't know that it was a single layer graphene. But here we see that in action, so the dissolved carbon comes to the surface, and the higher the temperature, the more carbon there is, and eventually the surface is covered with graphene. So that was the title, The Winner Takes It All. If you just heat it, maybe you get something different that you were hoping for. And here it's carbon, because the carbon binds strongest on the platinum 111. This does the same effects again seen in the UPS and in the intensity of the XPS, but this is what we already saw. So the intensity of carbon just goes up with annealing temperature. Those are the red, the black dots. So the intensity goes up with the annealing temperature. Then I will quickly flash through some of the recent work we did with Thomas Kreber. I have no time to go into details. This was just a qualitative study of DFT, so density functional theory, and calculating these small to bigger adsorbents, and finally the monolayers of graphene and HBN on different transition metal surfaces. But before that, I just very quickly mentioned this work I'm flashed earlier. So this was the HBN on iridium, so with two experimentalists, Peter Liljeroth and Fabian Schulz at the Aalto University in Finland. We did a project where they did some experiments, AFM experiments. So this is the moire of HBN on iridium. It's just some curves along at same position laterally, but different. and they could derive the height of HPN at different positions of the molar. And then this is the result of one of the DFT calculations. But the goal was to kind of benchmark the different approximations in DFT, so-called the exchange correlation functional. So those are the different approximations on this axis. So it's just different approximations, there's no continuity. And then the dots are the position, the height of the boron and nitrogen atoms above the iridium substrate. And the experimental values are the dashed lines, or these lines here. And so we compared which approximations give us good structures from the DFT. So these are very much what we want often from experimenters is to have hard data, and we can then justify the approximation that we use. Because DFT in principle it's exact, but we always need to do this approximation. So this is now the study that we did with Thomas. I said we calculated 12 substrates, these different adsorbents. And here's for example, the mismatch between the two. This is in percentage the mismatch of the lateral lattice constant HPN or graphene and the substrate beneath. So those are the 12 cases plus one. We calculated 2 forms of cobalt. And then adsorbents, well, we had the atoms B and N in the bulk on the surface, different positions, dimers, hexamers, and then the full monomer answer vacancy. But I have no time to go this. Here are just some numbers of the adsorb atoms and so on. What I want to show you is the energy diagram, what we derive at the end. So we have the boron nitrogen adsorbed here, and the reference is in the gas phase. That's the 0 electron volt. I'm sorry, you probably can't see there's no way to, no zoom. So this is energy scale in electron volts per one pair of boron nitrogen. So the gas phase is the black one, and then 3 panels, 3D metals, 4D metals, and 5D metals. And then we studied, I said, the adsorb atoms, dimers, hexamers, and the full monolayer. And one sees the main message is here that depending on the substrate, you have different binding energy of the atoms with respect to the dimers or hexamers. And in some cases, you even go up in energy to form the dimer on the surface. So then we expect, of course, that the initial growth is slow on this kind of substrate. And to end, I just mentioned we have recently started to study some adsorption of defects on the HPN, so at atoms in this case. And this is just at the surface. So this is the part that we initially started in freestanding HPN, and now we are doing the same on the substrates. And we use 2 different examples. The boron nitride on nickel 111 is actually commensurate, which means that they have the same lateral lattice constant, or very, very close to the same lattice constant. And also on copper, the lattice constant is quite similar, but the interaction is weak, whereas it's strong on nickel. So this is what we plan to do, is to use these 2 substrates to study the, for example, diffusion penetration of the boron nitride through the HPN layer. And this would be just the very, very last example. So here we have the initial state of diffusion reaction. So this boron at atom, which stands on the nitrogen. So this is now without the substrates still, and then how it's along the reaction path. Here it's just penetrating the HPN layer, and then here it's beneath. You don't see it, but the atom goes beneath. So this is the energy. We calculate the energy path and the energy for this reaction of penetration. And then this would be another reaction, and then we can derive these reaction energies. These are ongoing work, and as I said, we have started the same on the substrate. So this is on copper 101. This is the freestanding one. So we can study these reactions. Last but not least, I want to mention the co-authors, they have a startup called SwissBN, where they can sell samples of HPN. So they want to be able to sell those samples of growth, high quality and large samples of HBM, if anyone is interested. Okay, thank you.